Welcome to Business Calculus, and we're going to talk about the indefinite integral. All right, so before we start talking about the definition of the indefinite integral, we need to review some notation about derivatives. Notations for derivatives for functions such as y equals f of x come in Newtonian notation. That's where you use the little tick or the prime, y prime equals f prime of x, or Leibniz notation, and this uses what are referred to as differentials. The derivative of y would be dy dx, or we would write the derivative with respect to x of f of x, d dx of f of x, or we would write df dx. Differentials come into play in a lot of applications. You have already done this several times in your application of derivatives. For example, the difference quotient, which can be written y2 minus y1 divided by x2 minus x1, or perhaps f of x2 minus f of x1 divided by the quantity x2 minus x1. In other words, delta y over delta x. The little delta simply means a change or a small change, or the difference between two different points. And this is approximately equal to dy dx in differential form, which is the same as f prime of x in Newton's notation. Okay. Well, when we're integrating, we sometimes want to write the differential form in a slightly different way, and this notation suggests a relationship between rates of change in the dependent variable with respect to the independent variable. Well, how much more or less does the dependent variable change when the independent variable changes? And it turns out that it's the same as the value of the derivative. And this is referred to as a differential form. You've used this differential form in order to construct the linearization of a function that is differentiable, or to find the equation of the tangent line at a point. We use the symbol where we have the elongated s, the original Latin s, the sum or integral of f of x dx. We use this differential form to represent the family of all antiderivatives of a function. And we can write that the form integral of f of x dx is equal to capital F of x plus c if the derivative of capital F is in fact little f. It's important to remember that little f and capital F represent two completely different functions. One is the derivative of the other. Little f is the derivative of capital F. And by the same token, capital F is one of the many antiderivatives of little f. Of course, we know that all of the antiderivatives differ only by a constant, which is why we've written that. So the differential form at the top of the page is a differential form because, of course, it can be written as the one at the bottom, the integral of capital F prime of x dx. All right, so what we're going to do in this lecture is we're going to look at the indefinite integrals of our basic functions, polynomials, the exponential function, and the natural logarithm. The indefinite integrals of basic functions will look just like their antiderivatives because that's how they're defined. The integral of x to the n dx will be x to the n plus 1 power. You'll add 1 to the exponent divided by the new exponent, n plus 1, plus any real number, c. The integral of e dx dx will be the family of functions, e to the x plus any real number, c. And the integral of x to the negative 1 power dx, the integral of 1 over x dx, will be the family of functions, the natural log of the absolute value of x plus c, where x does not get to be equal to 0 since it can't be in the denominator of 1 over x, or an argument for a natural log. And integrals will have the same properties that the derivative had in the last chapter. If k is a constant number, a real number, and f and g are integrable functions, then the integral of a constant times a function will be a constant times the integral of the function. And the integral of the sum of two functions will be the sum of the integrals. This is something that we've already practiced with derivatives, and we will continue to practice with antiderivatives. So let's do a few examples to get a good firm idea of how to calculate some indefinite integrals. All right, before we begin, we need a little vocabulary. The expression between the integral sign and the differential is called the integrand. And of course, we have our differential. The differential indicates to us, among other things, the independent variable, just as it did when we were differentiating. All right, when we see something like this, we realize that there's a 1 that's not written. And so we can use that first property of integrals. And the integral of 5 times 1 dx is 5 times the integral of 1 dx. The antiderivative, the family of antiderivatives, would be x to the 1 divided by 1 plus c. And we're tempted to write 5x plus 5c, but remember that c is an arbitrary constant, and 5 times an arbitrary constant is just another arbitrary constant. And so we write our answer in the following way. Let's compute a few more to get the right idea. The integral of 9 e to the x dx would be 9 times the integral of e to the x dx. And the family of antiderivatives for e to the x would be e to the x plus an arbitrary constant, not 9 times an arbitrary constant. Okay? The integral of 5t to the 7th dt would be 5 times the integral of t to the 7th dt. We would use the power rule for integrals. Add 1, divide by the new exponent, and get 5/8 t to the 8th plus c. Let's try a little bit longer polynomial. Now, I don't expect you to write this in your own notes or when you're taking quizzes or tests, but it helps to do this slowly the first time. Remember, the integral of a sum like this, just like derivatives, is the sum of the integrals. So we will have 4 times the integral of x cubed dx plus 2 times the integral of x dx minus the integral of dx, 1 times dx. And we'll obtain, let's see, if we use the power rule, we'll have x to the 4th divided by 4 plus 2 times x squared divided by 2 minus x plus, not minus, a constant. We can simplify this expression because 4 divided by 4 is 1 and 2 divided by 2 is 1. And we have our solution. The integral of 2 e to the x plus 3 over x quantity dx is going to be 2 times the integral of e to the x dx plus 3 times the integral of 1 over x dx. The integral of e to the x dx is the family, okay, so we're going to get 2 to the x plus a constant, which we'll put off until we get to the end, plus 3 times the natural log of the absolute value of x, plus our 2, which we'll combine into one arbitrary constant. It's helpful when you're integrating to rewrite things in rational exponents so that you can use the power rule for integrals rather than denominators or fractions or roots. So we'll write 4 divided by x cubed is 4x to the negative 3. So now we can use the power rule for integrals. Add 1 to the exponent and divide by the new exponent. Let's see, 4 divided by negative 2 is a negative 2. So you could write it like so, or as a fraction. Let's let you look at that for a second. Okay. As in the last example, integrating a complicated expression like roots we're better off rewriting this as a rational exponent. So 5 times the integral of u to, let's see, squared, but cube root to the 2/3 power du. Now we can use the power rule for integrals. 5 times, well, u to the 2/3 plus 1, that's 2/3 plus 3/3. 5/3 power is the new exponent divided by the new exponent. 5/3 plus a constant. We can simplify this, dividing by a fraction. We invert and multiply. U to the 5/3 plus c. And we get our result by simplifying. We have 3 u to the 5/3 plus c. Let's try the next one, number 8. When we see a complicated rational expression and the numerator is of greater degree than the denominator, often it helps to just divide. Remember that this is just x cubed divided by x squared minus 3 divided by x squared dx. Let's see, x cubed divided by x squared is x minus 3, and we'll use a rational exponent to x to the minus 2. I think we can write our minus 2 a little better. dx. Okay, now we're ready for the power rule. X to the 1, let's see, so x squared, 1 plus 1 divided by 2, the new exponent, minus 3. Now we add 1 to the exponent. Minus 2 plus 1 is minus 1 divided by the new exponent plus c. So we get x squared divided by 2. Minus a minus is plus. 3, a negative exponent means I belong in the denominator, plus a constant c. 2 more. We want to continue giving examples of properly using rational exponents in order to simplify our computations. Let's see, we have 2 times the integral of what? Now x to the 1/3, but it's the denominator, so this will be a minus 1/3 in the exponent dx, minus 6 times the integral of x to the 1/2 dx. Now we can use our power rule for exponents, so we have 2. Now let's see, minus 1/3 plus 1 is minus 1/3 plus 3/3, so that's going to be x to the 2/3 divided by the new exponent, 2/3, minus 6, x 1/2 plus 1 is 3/2, x to the 3/2 divided by the new exponent, 3/2, plus c. Well, we'll invert and multiply. 2 times 3/2, x to the 2/3, minus 6 times 2/3, x to the 3/2, plus c. All right, so 2 times 3/2, so we get 3 x to the 2/3 minus 4, 6 times 2/3, x to the 3/2 plus c. You can pause the video if you want. Take a look at this very carefully. Make sure that you remember your use of rational exponents and how to divide by fractions. And finally, multiplying products, as we will learn in the next section, is much more difficult than multiplying terms because the integral of a sum is the sum of integrals. So we'll just expand this and then integrate. X times the quantity x squared plus 2 will give us x cubed, x times x squared, plus 2 times x dx. Now we can utilize the power rule, so we increase the power by 1, x to the 4th divided by the new exponent, plus 2 times, we'll increase the power by 1, x squared divided by the new exponent, plus c. The only real simplification we can do is 2 times 1/2. And we're done. Now one for you. Are you ready? Find the indefinite integral. Find all possible antiderivatives for the expression, the integrand, quantity x squared minus 2 times the quantity x plus 3. I'll show you your answers in a moment. All right, so we have 5 of them here. Is it the first expression, which is the quantity x cubed divided by 3 minus 2x, times the quantity x squared divided by 2 plus 3x, all of this plus an arbitrary number c? Or is it the expression x to the fourth divided by 4 plus x cubed minus x squared minus 6x plus c? Is it the expression x to the fourth plus x cubed minus x squared minus 6x plus c, which doesn't differ from the one above it by very much? Or yet another variant, x to the fourth divided by 4 plus x cubed plus x squared plus 6x plus c? Or is it none of these? You decide. Thank you.